Russia, from the Moscow State University, did a PhD from Usmania University. Then she did postdoctoral work at Inter-University Center for Astronomy Astrophysics, IUCA, where even Shoshan was there as a postdoc, right? Later, yeah. While she was doing a PhD, she was already a postdoctoral fellow there. And yeah. And then she taught at Usmania for a while as a part-time teacher, then in Wafakamja College of Engineering, then finally at Mano. Yes, so we are happy to have Priya talking to us about certain aspects of this archival data and the potentials of it.
Thank you. Thanks a lot. And actually, the next talk is at 12:30. So I will speak a little lesser and maybe add the remaining part to my next talk if there is no time. Okay. So actually, this talk I will talk basically again related to the project which we are talking about, AstroSprint, because the purpose of this whole thing is about astronomy archival data and its potential. And that's what I'll basically be talking about as to what is the astronomy archival data available, which you can use for projects. Sushan spoke about basically projects with neutron stars. I'm going to talk about projects with other areas, which I'll just approach, right? So. So the data that we'll talk about in astronomy would basically be digital data, right, which you are nowadays all seeing. And like again, she had mentioned that the kind of digital data available in astronomy nowadays is very, very large. It's a very large amount of data. So there are some things you do not know about VISTA as well as LSTP, but you can see that there are very large amounts of data, and therefore for astronomy, there are actually data centers where data is hosted in very big systems, and they can be accessed through various means. They can be accessed through what is called virtual observatory tools, which Professor Hasan will talk about today afternoon. What are different virtual observatory tools with which you can access the data? And you can also access the data via Python programs. So you can have Jupyter notebooks in which you can directly query the data, get the data, do some analysis on it, and go ahead in that way, right? So even that is possible, right? So what is the kind of data that's available? One data is images, and these images can be in the form of what we call data cubes. So for example, if I have a picture of this room in supposing 5 filters, 5 different filters, I put them all one behind each other, so it becomes like a cube, right? So I have many images together, stacked together, and they are called data cubes. The data can be in the form of catalogs, which are tables, right? You can have tables which has, X, Y, brightness, whatever, some parameters. The data can be spectra, because we deal with spectroscopic data in astronomy. The data can be time series data. By time series, I mean, supposing you have a variable star. So you observe its brightness at different times, and that is called time series data. If you are observing polarization of these objects, it could be polarization data. So there are different kinds of data available. Now, the first kind of data which we can talk about are images, digital images. This is the regular images which you have on your cell phone, right? Digital image. And what is that image? That image is basically like a matrix. Okay, it has XY grid, and you have a certain brightness on a certain pixel. So you have, it's like a 2-dimensional array. So if people who are already using Python programs, etc., this is like a 2-dimensional array where you have pixel values, right? Each point is a pixel value telling you what brightness it is. Now, in astronomy, we do it with certain filters. It could be a red, blue, or green filter, or whatever is the filters you are using, or we also use often artificial colors for astronomy. This thing. Often the artificial colors are related to the wavelength in which the observations are made. Now the observations could be point sources, for example stars, or they can be extended sources, for example galaxies. And these objects are taken with what is called CCD, charged coupled device. So all your cell phones, all these laptops, etc., all have these, not laptops, sorry, cell phones do have it. Your digital camera has a CCD. And what does the CCD do? CCD is like a bucket, right? Where at every point it measures the brightness, right? So supposing you have rain falling, then on different points of the bucket you collect water, and how much ever water you collected is your photon count. How many ever photons you get at different positions. And if you do it with different filters, you can do it with red filter, blue filter, green filter. You have to do all that so that you get a colored image. So generally what is done is you have 50% of the filter. If you take a colored image, 50%, which is there on your camera, 50% of the big pixels are sensitive to green light, 25% to red light, 25% to blue light. And this is what is used in all our digital cameras, camcorders, scanners, etc. That's how we actually get digital images. In astronomy, what we do is slightly different. We take one image with red, take an image with green, take an image with blue, and add them all up together. Right? But in your cell phone, for example, you have something like this. You have a filter array which has a mix of red, blue, green filters, so that you get a colored image. So in astronomy, when you take images, see this is a colored image. This colored image is basically obtained by taking 2, 3, or 4 colors in with different filters, and you add them together to get a colored image. That's how you get a colored image. Now, obviously, in these, often you have artificial colors. So what is in longer wavelength is often blue color, in red light, and what is in shorter wavelength is blue light. So accordingly, you can color the images artificially. And for astronomy images, we have a format which is called FIX, which is the flexible image transport system, which is a certain format in which images are kept. So we do not keep it in JPEG format or PNG format. We put it in this format called FIX. So this is again the same thing what I was saying. So an image actually is like a matrix. You just have a 2-dimensional array which has different values, and that will give you an image. Right? That is how we get the image. The brightness also is certain brightness of the pixels. In astronomy, we will show you that you can use different software to see the image better. So for example, if the original image is this image, you can do, this is called linear scaling. Supposing the image, I know that the brightness is within a certain range, I can make cutoff so that the brightness is in a certain range so I can see it better. In this case, I take the square of every pixel value to enhance the value. So this is called square scaling. This is called this is linear scaling. And for example, look at this image. This is an image of a young cluster. This is called NGC 281. And you can see there's some amount which is purple, there's some amount which is red, and this is like that. But actually this image is a composite image. This is a mixture of different images. This is the same thing in optical light. Okay, this is 281. It's also called the Pac-Man Nebula, which is 281 in optical light. If you were to see it in Spectra, which is infrared light, it looks like this. If you were to see it in X, this is again Spectra image. And if you were to see it in X-ray by Chandra, you will see an image which looks like this. Now what we do is we add all these images together, and with that we get this image. So the image which I showed you, this purple part is coming from Chandra, which is short wavelength, high energy, X-ray radiation, while the red color is coming from Spitzer, which is long radiation. So you have all these images added together to give you this colored image. And like I told you, this image is artificial colors, but the colors are indicative of wavelength. So blue is shorter and red is longer. Now, based on this, we actually do lots of image processing in astronomy. That means if you have a digital image, you can do many things to the image to process it so that it can give out certain features. But we won't talk about that now today. You can also deal with spectra. What are spectra? Spectra are, you will have done it in chemistry, you have light passing through a disperser. You have to disperse the light in some way. You can disperse it with a prism, you can disperse it with a grating, you can disperse it with different things so that you can see all the wavelengths of light, right? So this is intensity versus wavelength for the spectra. And again, the spectra also, you can make data cubes of them where you can add up spectra. you can actually take spectra. Supposing you have a set of stars, a cluster of stars or cluster of galaxies, you can take spectra of individual stars or individual galaxies and add them all up together, right? This is another example of data, which is catalog data. And so you can see over here, this is catalog, where you have tables, X, Y, Z tables, and things like that. So this is catalog. To handle that catalog data, there is a special software in Virtual Observatory called TopCat, which sir will show you today afternoon. You'll see that later on. Time series data, again, I have, variable data, so you can see it like this. And like I told you, there are different tools used to observe images. There's something called DS9, which we'll show you in the afternoon. For catalogs, there's something called TopCat. For normal programming, you can use Python, you can use Jupyter Notebooks, whatever you like. And there are many modules and libraries available specifically for astronomy, AstroPy, and related lots of libraries which you can use to actually access astronomy data. And obviously, they should not be used like black boxes. You have to understand the tool so that you can use it properly. With every image or with the data, you also have what is called metadata, which describes the data. It gives you information about the data. For example, from which telescope, what exposure time, various details about the data, which filters, etc. So what is an astronomy archive? So in astronomy, we have archives, which is organized systematic information about the sky, which is kept in this, like I told you, in those data centers. And that is what we are going to access, the astronomy archive. Now, astronomy people tried to archive data since a long time, from the times of Hipparchus, where he'd archived data for 850 stars. This is using naked eye observation, Tycho Brahe too. And then when Kepler derived his laws of Kepler, Kepler is the first example in principle of using archival data, because he used Tycho Brahe's data and he used that to match with his theoretical calculations, on the basis of which he derived his laws. So in principle, I would say he is probably the first user of archival data to actually get something in theory which was not known of, which actually shows you the potential of archival data, that if somebody has observed something a long time back, there is still many ways in which you can interpret that data, right, to actually understand what is actually happening. And that's what actually Kepler did. Tycho had data of the orbit of Mars, the orbit of Jupiter, right, the brighter planets, and he actually used that to, get his Kepler's laws. So that's already a very encouraging thing. After that, a lot of other people also always made catalogs to actually, so there's the Messier catalog. So you'll see many astronomy objects are mentioned as M1, M2, M3, that is Messier objects. Or there is a new general catalog, NGC catalog, the Priya catalog, various catalogs. Now, one of the earliest attempts in modern times of cataloging data was the Palomar Sky Survey. So the Palomar Sky Survey, this observatory, they at Mount Palomar, what they basically did is that they used photographic plates to image the sky. So there were 2,000 photographic plates to image the sky. And in the 1990s, they digitized all these images. So therefore, that is called the DPOS survey, which is a digital Palomar Sky Survey. Now, digital data also, like I said, it uses the CCDs, and CCDs have a linear response to the data. And a lot of important citizen science projects. I've been also working a lot on citizen science projects, because lots of these archival data centers have a lot of data, and there are not enough astronomers to do it. So there are many citizen scientists. Some of them you can even download like an app on your phone. You can download it like an app on your phone and actually analyze data from very good telescopes to actually do citizen science. So citizen science are projects in which you try to involve regular citizens. They needn't be students of physics and math, just citizens who can actually look at the data and do things with that data. CCDs, sorry, I think this got slightly mixed, but the CCDs are the source for digital data, which we basically use in astronomy and other wavelengths too. Now, with astronomy, technology has constantly been going hand in hand. We have a lot of developments in technology which have been side by side, which are happening with us. I would request you to tell me when it's 12:55. Okay. Yeah. So we have this thing. So like I mentioned, we have these various citizen science projects with which you can actually work with Astronomy Archive. And there are various data archives. I will share this PDF file so you can see this list. There are various data archives and different ways of accessing these data archives. Okay, I won't go into details, but in the tutorials we may use it. Another important data archive is the Hubble telescope data archive, but this also not only has data of the Hubble Space Telescope, but also will have data of the James Webb Telescope, which has been launched in December last year, which very soon, on the 12th of July, we'll start off with the first images for James Webb. And these are earlier missions, space missions. This is the test mission for exoplanets and the Kepler mission, etc. All the data is available on the Hubble website. And it has various good features, lots of data. Another data set, which especially I have been using a lot of late, is the Gaia Satellite. This is ESA, the European Space Agency. They sent off the satellite with which they are observing 1 billion stars with very good photometry, astrometry, as well as spectroscopy. Excellent resolution. If you had a 1 rupee coin on the moon, you would be able to see it from the Earth. That's the kind of resolution you are getting. And this is also important data. And my students, we are all working on Gaia. Similarly, the GMRT, where Sushan works, this is a giant meter radio telescope. Like we mentioned to you, initially when people observe, the data is there, it's proprietary data. After some time, after a certain period, it is kept for anybody who wants to use. So you can also access the GMRT archive and actually take data from the GMRT archive. Chandra is an X-ray telescope out in space, and the Chandra data is also available on its archive. This is the Sloan Digital Sky Survey, which observes the sky as well as in 5 photometric bands, as well as with spectroscopy. There are many more related surveys, and one can access this data to SDSS. I'll just fast go through some possible projects. We don't have too much of time, but I'll just do some. So one, like I mentioned, was citizen science projects. There are various citizen science projects. For example, some of you all may have seen the movie Don't Look Up, which is basically about an asteroid which is going to hit the Earth, right? Now, these asteroids are not very bright objects, and they could be anywhere in the sky. And therefore, there are special citizen science projects, like there's one for asteroid searching, where we actually look at data and look for asteroids in the data. There is also a citizen science project on looking for planets, looking on galaxies, looking for exoplanets, etc. I can tell you these details later on. So, for example, with exoplanet data, you can use Kepler. Kepler is a space telescope as well as TESS. This is a transiting Earth satellite. And with this, you can actually look for exoplanets. So, what is an exoplanet? An exoplanet is a planet that is going around a star other than our sun, outside our solar system. And if you remember, in 2019, the Nobel Prize was given to these two gentlemen, basically for the discovery of a star like an exoplanet around a star which is similar to the sun. And so basically different techniques are used to look for exoplanets: radial velocity, microlensing, transit photometry, direct imaging. The projects, what basically Kepler and TESS do, they basically look for transit photometry. By transit photometry, I mean, I look at the star, time series data, I look for the fall in the brightness of the star and get this dip, right? And we can use this data to actually get the parameters for the planet. So for example, you look at the sun, at the star, see the fall in brightness, and that will give you the details about the planet. So you'll see that. So if you have a planet going in front of the star, you'll have a fall in the brightness, and you can use this this dip to actually estimate what is the this thing. So this is one of the projects which was done in the earlier sessions, which is done with looking at a planet which has a small, a star which has a small planet. You can see the dips coming because of the passing of the planet, and for which you can actually find out this thing, right? So this is the microlensing. So the light curve which you will see is slightly different if it is microlensing or various other things happening. So with microlensing, you will see certain dips. So the Kepler mission is another mission that is the same, which will also, and K2, again, which is the successor to Kepler. And with that, you can actually look for exoplanets. So one of the projects is actually looking for exoplanets using Kepler K2 test data, right? using what we call light curve analysis. So finally, you will get the mass, the radius, the density, and the temperature of the planet for that star. The other project which students did was using Gaia data as well as Hubble Space Telescope, which is HST data. So one project was using HST data for a globular cluster. Look at the image, and they did what is called aperture photometry, measure the brightness, and using that they find out the distance. This is aperture photometry. You look at every star, measure the brightness in every star using this software, and using that they plotted what are called color magnitude diagrams, and we can use this to get the distance to a globular cluster. The other thing was using Gaia data, you can actually look at star clusters, stellar extremes. That is, for example, using TopCat, you can use TopCat, and supposing you actually query it for Gaia data. If you have a star cluster, this is proper motion space. Proper motion is velocity of the star. You will see a certain lump over here, which is the indicator of a cluster. And you can actually use this. This is the cluster, which is this blue thing over here. And we can use this to get parameters of the cluster, the distance, this is the velocity of the stars which belong to the cluster, which is showing you a velocity diagram. And with that, we can actually find a cluster. So you'll see, we can find out this thing. There was also a project done on membership of cluster stars using Gaia data, for which we have distance photometric spectroscopic data. And we also did a project with membership data. Actually, this was also part of Mudassir's thesis work also, which we are doing. And so this is not just AstroSprint, this was a student's project as well as part of PhD. So we are doing this to actually do machine learning techniques to find membership for clusters using Gaia data, as well as getting distances. I won't go into this detail. What is the time? Okay. So these are star clusters. We won't go into this detail, but you can actually study star clusters, get the members, get their distance, get their ages, get their reddening, and you can use that to actually find out parameters for clusters. So those are also, many students did projects with globular clusters, with star clusters using Gaia data as well as HST. Another good project which some students did was on the study of external galaxies, observations of external galaxies, which Professor Hasan will talk about more in detail. I'll just tell you about the project. So this is essentially using Hubble Space Telescope data. In principle, you can also use SDSS data. Hubble Space as well as SDSS data can be used. So this was also part of PhD work of a student who actually, this is part of one of my papers using GalFit. This is a software used to actually observe galaxies to find out their different components. So for example, you can see that this is the original image of the galaxy. But if we do modeling of the galaxy for different parts of the galaxy, using the software, you can actually identify spiral arms in this galaxy. You can't see spiral arms very nicely over here, but in this you can clearly see this thing. So by using the software called GalFit, we can actually use images of galaxies to see further features in the galaxy. So for example, you can see if it has a core, if it has a double core. There are some galaxies which have double nuclei, or if they have spiral arms, or any other features, if they have bars, or many other features, you can see it with using GalFit. So that project was basically a project using GalFit, which many students also did with Astronomy for archival data, using GalFit for Hubble Space Telescope data. And there are many more projects that people can do with gravitational lensing as well as with dark matter. These were done by Timothy Hamilton, who will be doing a session tomorrow morning. He will do a session tomorrow 9 o'clock to 11 o'clock. Timothy Hamilton already did these projects on gravitational lensing as well as dark matter. And they are already available on YouTube, because all the things that we do, we immediately live stream it on YouTube. So the detailed step-by-step guide as to how to do the projects with gravitational lensing, with dark matter, and many more data sets which Timothy Hamilton did are available on our YouTube website as well as our website. And you can actually see them very nicely, step to step. He's going to do it. Tomorrow, he's going to do a session from 9 to 11 in the morning, which will be basically on integral field spectroscopy. Okay, that is, he's not covered that topic, but he'll be do a 2-hour hands-on session tomorrow morning from 9 o'clock to 11 o'clock on basically on integral field spectroscopy. So please attend that one. For that one, you will need to have your laptop with you and you have to do it hands-on online. Okay. So that will be tomorrow morning, 9 to 11. Timothy Hamilton, he will do that. The earlier projects are available on the net. So I will actually conclude with this, that the world is always open. It's waiting to be discovered. We obviously in these 3 days, we are not going to cover all the data sets and all the possible projects that can be done with this data. But obviously the idea of these workshops is to give you an idea of what is the possible available data, what are the possible projects you will work on. And then once you decide to work on a project, obviously it's a different story, right? Then there is a lot of work you have to put in, and then you have to go into details about each of those things. But in these 3 days, we are not going to get time to go into the details of all these things. 3 days is basically to introduce you to everything, right? And after that, the students who are interested, online as well as offline, they can get in touch. I will then share Google Forms where you can decide as to which are the projects which you would like to work upon. Different speakers will talk about different possible projects. And accordingly, you all can decide which are the projects which interest you and which do you want to work on. Obviously, this is all optional, right? This is not part of your syllabus. It's not part of your exam. It is something which you will do because you want to, right? So, or if you want to pursue a career in astronomy. And even a reason why we are doing a lot of this thing, because if you, for example, even just working with Python coding, we have some students who are from MSc, who are just MSc Maths, who are doing Python coding. You could just use astronomy data to improve your coding skills, right? Because you can write programs, look at the data. With astronomy, you get beautiful images, you get nicer things to look at, right? So you can work with that data. In that sense, you will learn how to do Python coding, how to handle software, right? You finally do not have to become an astronomer, but at least you can learn how to handle software, how to deal with these things. So that is the basic purpose of the workshop and the theme of the whole thing, right? I also want to announce that on day 3, that is on Sunday, we are going to have a visit to the observatory. So please register your name with Mudassir if you want to come to the observatory, because we have a single bus which is a 50-seater bus, only 50 seats available. So Mudassir will decide who all are sitting into the bus, right? So please tell him, catch him, and ensure your place in the bus. If you come with us, we will provide you dinner also. Don't worry. Okay. So that will all be done. Now the next speaker we have at 12:30. It's 12:30. Okay. So the next speaker we have just now is Sami Deb. He is speaking to us from Niels Bohr Institute, Denmark. Okay. And he will be talking, he'll be giving the talk now 12:30 to 1:30. After that, 1:30, we'll have the lunch break. And then we will assemble again over here at 3 o'clock. And his second talk will be from 3:30 to 4:30, Samidip. Okay. After that, we'll have tea break. Then we'll have Sir's talk on virtual observatory tools. And then we have a talk from 6 to 7, which is by Hans Moritz, who is from MIT. And he will talk to us about Chandra. Chandra data is run with a software called Chow. So he will actually help us hands-on how to install Chow. So I'm now going to wait for Sami to come online, and we'll